Yes, so welcome to SPCL Bcast. We are super happy to have been able to convince a good old friend, Rob Schreiber, and Natalia from Cerebras to talk about their newest developments in Cerebras systems. So Nikolai, go ahead and introduce our guests.
Okay, yes, thank you, Torsten, and thank you, everyone, for attending. It's a great pleasure to introduce Rob and Natalia, who really actually don't need much of an introduction, but I will give one anyway. So Rob is a distinguished engineer at Cerebras, where he works on architecture and programming systems for AI and science. He has far too many prior accomplishments for me to list. He's an ACM fellow, a SIAM fellow. He has received the Career Prize from the SIAM Activity Group for Supercomputing. He worked on the sparse matrix representation for MATLAB, high performance Fortran, the NAS-CG parallel benchmark, and many other things. Natalia is Director of Product Machine Learning at Cerebras, where she leads market application and algorithm analysis for machine learning use cases. Previously, she was a Senior Research Manager at HP Labs, where she led the software and AI group and worked on performance characterization for deep learning workloads, Monte Carlo simulations, and many other things. She was previously an associate professor at St. Petersburg State University and a lecturer at St. Petersburg Computer Science Institute. Without further ado, Bob, Natalia, please take it away. Thank you.
Well, thank you, Nikolai. Thank you, Torsten, and thanks all for attending. Hi, Danielle. It's a pleasure to be here. It's my second visit to Zurich. First one wasn't virtual. Good. Well, you know, at Cerebras, we're doing interesting things that take us to a world beyond Moore's law. So I'd like to tell you what we're doing and then talk a little about HPC and AI and what the future of computer architecture may mean for them. I'm going to hand off to Natalia after about 25 minutes. So anyway, let's jump in. People claim Moore's law will never end, but I don't think so, and neither does Moore. I was in the room at the Computer History Museum when Carver Mead interviewed Gordon Moore and asked him the question, and this was Moore's answer. We're at a few nanometers. The crystal lattice of silicon is 50 angstroms, so we've got a little ways to go before we're completely out of gas, and we have to figure out a way other than atoms to make transistors. Well, so if Moore's law is ending, let's take a quick look at the whole history of HPC and of computing in general. This is the performance of the world's fastest machines from the pre-computer era to the present. From the beginning of the computer era, which is, can you see my cursor? Around, yes. The middle of the Second World War, here you have sequential computers at 10 to the 5th, and then we get up now to about 10 to the 17th flops. So 12 orders of magnitude, pretty impressive within a little more than my lifetime. So one lifetime, 12 orders of magnitude, not bad. And notice a straight line on this plot means an exponential growth. And of course, the fastest exponential growth is the green line, which is the VLSI, Moore's law, Dennard scaling era. Dennard scaling died. So we're really already, and Moore will run out of gas. So we're into a post-Moore era already. As you see, we're still growing. So there's still an exponential, it's just with a different lambda. Do we need faster machines? Yeah, we're at exaflop. Will it end there? The answer is we need much faster machines. Here's a whole long list of evidence that we need faster machines, from the fact that the most powerful machine in the world now costs $1 billion, and it seems to be worth it, to artificial general intelligence, the flood of data, and on and on and on. Many reasons why we could do a great deal more with another 3 or 6 orders of magnitude of added performance. And here's just an example of the memory requirements for large natural language neural network models. They're growing without bound. We can barely do these today. These take heroic efforts. So necessity, yes. Invention, let's see. Well, one important trend is the abandonment of the one-size-fits-all, everything on an Intel x86, we just make clusters of those. That really wasn't ever a great idea, but the very rapid development of those Intel chips would put everyone else out of business during the Moore's law Dennard scaling exponential. That stopped, has opened the doors for optimized architectures, and we have tensor cores and TPUs and GPUs and neuromorphics and whatever coming into play here for HPC AI and other domain-specific architectures. And we have a new thing, which is what Cerebras has done, wafer-scale chips. We may also have analog and neuromorphic approaches. We may have quantum approaches, but you can't really buy anything today of that kind and do anything with it. Here's the Waferscale Engine. Here's the Waferscale Engine Part 2. There's another great picture of this with Natalia holding it that you can find on the web. It looks exactly the same as the Waferscale Engine number 1. It's the same size wafer with the same array, 7 by 12 of reticle flashes. But this one has 2.2 times as much stuff, 2.6 trillion transistors, 850,000 processor cores, and I'll tell you about those cores soon. And I'll tell you about the wafer soon and how we built it. So it's about 55 to 60 times the size of an 800 square millimeter world's biggest GPU. What does that buy you? Well, 56x in size, over 100 times as many compute cores. The on-chip memory is much greater. Half of the wafer is SRAM memory. You'll be pleased to know, since you're HPCers, that it's completely distributed memory. There's no shared memory on this, not a single bit. The SRAM memories are basically like all the memory is L1 cache. There's no cache hierarchy. The total memory bandwidth is unbelievable. It's enough that you don't need a cache. Fabric bandwidth, also unbelievable. And that's for the network on chip. Now, of course, I'm cheating to a certain extent because the marketing department created this. And I'm not talking about off-chip fabric or off-wafer fabric and off-wafer memory. I'm talking about the on-wafer. But the point is the wafer is so big you can do a whole job on one wafer. So let's talk about how we built this thing. They said it couldn't be done. It was tried in the 80s by a startup known as Trilogy, who spectacularly failed and sank and took a lot of money down with them, including Gene Omdahl. He was one of the founders. So here's the wafer. The first issue is how do we connect? How do we connect across the wafer? So these spaces between die normally get cut, and they're used by the vendor TSMC for whatever they do to measure and test what's going on in the fabrication. So we collaborated with them to be able to lay down a very dense wiring across those lines. The upshot being that processors within the same die have no more bandwidth between them than adjacent processors in different die. There's just enough wiring in the spaces. So they're 84 die, tightly connected for some reason. Unfortunately, PowerPoint's slow. Defects. The conventional wisdom is you can't make big chips because the defect density on the wafer is constant. The bigger the chip, the greater the chance it won't work. So we don't. We make zillions of very teeny cores. And we have enough redundant wiring that if a core is bad, like this black one in the middle, we can route around it and restore a logical two-dimensional mesh, even though physically we have gaps. And we have extra rows of cores in every die to accommodate that. So we yield very good wafers with logical 2D meshes that are near the maximum possible, which is about 600 squared. You have power and heat and other things that have to be delivered to and removed from, and it's very challenging. The wafer has no greater power density than a chip, in fact, a little less, but it's so large that the total flux of current and power is large, and then the flux of heat out has to be large. And that can't be brought in any way except through the face of the wafer. There's too much resistance if you try and bring it laterally across the wafer. So power comes in through the main PC board. There's a great deal of current. With 20 kilowatts at roughly 1 volt, you have many amps. So it comes through a flexible connector into the wafer, the silicon wafer, and then there's a cold plate held very tightly to the back. And the same is true for the water. You can't bring the water in from the side, too much flow resistance. So the water comes in the third dimension as well to sustain both the power in and the heat out. The thermals are interesting. Of course, this thing heats up at 20 kW. It gets warm. And unfortunately, silicon doesn't expand at the same rate as PC board. So aligned contacts become misaligned with thermal expansion somewhere across the surface of this 8-inch, 200 millimeter wafer. So we have to find and reject and find again flexible connector technology that actually worked reliably to connect contacts even though they moved laterally with respect to one another. So we've solved these and a host of other engineering problems in order to reliably build this system. We had to invent a lot of stuff to do that. Here's some photos of work in our lab, which show, measurement devices and various things that were built for testing and measurement and assembly to do this kind of a wafer scale thing for the first time. This is what the chassis looks like. You have a front panel. You have fans for blowing air into a heat exchanger. You have pumps for pumping water in a closed loop to take heat from the wafer to the heat exchanger. You have power supplies. All of these are multiple and redundant. All of that power, water, and air moves through in this direction to what we call, here's the heat exchanger, and here's what we call an engine block, which is where we have the sandwich of the cold plate PC board and wafer. Let's talk about programming it very briefly. We want to train neural networks. That's use case number 1. To do that, we allocate a rectangular subwafer. We call them Colorados. A rectangular subwafer per each layer of the neural network. And we lay them out on the wafer in an arrangement like this, and we connect them to implement the layer-to-layer communication, but we also have a great deal of interconnect within a Colorado for the communication between the processors that are implementing a single layer. So part of the compilation, which is done automatically, is to do the placement and routing. And with this, we implement a pipeline version of gradient descent in training. We send a stream of mini batches in. They flow through in the forward direction. Gradients flow back. And as gradients arrive, they update weights. So it's not exactly stochastic gradient descent because there's a delay between several mini batches have passed through before the gradient comes back from mini batch I and updates the weights in a given layer. You're already at mini batch I plus 25 or something on the forward dimension, but it works, it converges, and it allows us to employ the full parallelism of the wafer. This is only one strategy. One could do layer at a time type things, or data parallel layer at a time type things. There's still a great deal to do to find the optimum way, but this is the current mainstream approach, and it's working for training neural networks on a wafer. Let's talk about uses that people are putting this thing to, the customers, and what they're doing with it. Briefly, Natalia may have some more to say about that, but we have systems at Lawrence Livermore National Lab where it's being used for simulation of this giant laser system they have called the National Ignition Facility, or also called, it does inertial confinement fusion. A lot of fancy words. It means you shine enough lasers at a target that it can be raised to the temperature at which fusion occurs. Part of that is understanding the atomic physics, which used to be done with a physics-based simulation that was very slow. And it's been found that a neural network is capable of doing that job quite accurately and much faster. And so Livermore has connected through their InfiniBand network a CS1 system to their Lassen supercomputer. And the idea is that right in the loop of a time-dependent PDE simulation of the NIF, they're going to stream data for inference, in inference mode, stream data to the CS1, which will apply the neural network, predict the cross-sections and interactions between light and neutrons and atoms, and send them back. And they achieved the 37x speed up over 1 volt using the CS1 for this. They are quite keen on this idea of a future of heterogeneous clusters. We now have homogeneous clusters of heterogeneous nodes, but they're looking at clusters with multiple node types, Waferscale engines, GPUs, CPUs, other AI optimized hardware, and figuring out how best to employ that combination of tricks for any given application. They have notions about neural network models both in the inner loop at every time step, and then in an outer loop every so many time steps, and then in a sort of campaign strategy, deciding what's the next simulation to do in a long sequence of simulations. So they're all in on figuring out how to make the best use of AI models and neural network models to support what they're doing. We have another system in Argonne National Laboratory, which has a number of projects, some involving cosmology and some involving biomedical applications. There's a big project around artificial intelligence and cancer research. That's the CANDLE project. There are several different directions for the use of neural networks, and the first one that they've used the Cerebras for is for the drug response issue. So you treat cancer with not a drug, but collections of drugs, combinations of drugs, and there are many, many, many in the pharmacopoeia. And then if you're looking at combinations of several of those, you have an exponential growth in the number of possibilities with the number of drugs and their dosages that you could use. And there's no way to experimentally try all possibilities. So one has to prioritize. And previously, I presume it was the intuition of researchers. Well, let's see what AI can do. So they're trying to do that. And they've trained neural networks to predict the likelihood that drug combinations will be active against certain cancer cell lines. And that's the work they're doing with good results on the Cerebras. But now let's look at another thing, which is the interesting in its own right, and it allows me to describe some more details about the architecture of the wafer and the processor. And that's work we've done with NETL, the National Energy Technology Lab. That's another US Department of Energy lab. This one is in West Virginia. They do combustion simulation. Well, and their combustion simulation involves solution of fluid flow with a three-dimensional regular mesh using an implicit time-stepping method. And so they have linear systems on a mesh that they have to solve at every time step, multiple linear systems. So we're going to focus on that. How do you solve AX equals B, where A and X are distributed across this three-dimensional mesh? And they use a Krylov subspace method, the biconjugate gradient stabilized method, but it's from an implementation point of view, Krylov subspace methods all look the same. So the first question is, how do you map the mesh to the Waferscale engine? Well, we have a two-dimensional mesh of processors, and they have a three-dimensional regular mesh of points. So we map two of the mesh dimensions to two of the processor dimensions. Let's say we have a 600 by 600 mesh, and we have a 600 by 600 by n mesh, where n might be 600. In fact, in what we did, it was 1500. So each processor will hold a one-dimensional array of 1500 grid points. Now, the finite difference stencils that they're using are 7-point stencils. So in order to carry out a matrix vector product, you have to bring in the 6 neighbors. You have to combine 7 grid points. So a given processor, which has all of the points in the z direction, will have to bring in all of the points in the z direction from its 4 neighboring processors, shown here. So there will be interprocessor communication, and there'll be memory to communication. Both of these are bottlenecks. You couldn't possibly use this decomposition on a conventional machine because the memory would be too slow and the network would be too slow and too much latency. It's way too fine granularity. But on the CS1, it works like a charm because we have full bandwidth communication and full bandwidth memory. The building blocks for any Krylov subspace method are this the communication to do matrix vector, and then some XP operations on vectors. These are distributed vectors, but a distributed XP is just a bunch of local XPs if everybody knows the multiplier alpha. And then the way we get the multipliers alpha in these is to do global dot products, which involve local dot products followed by all reduce operations that you're very familiar with. So these are the interesting ones, the matrix vector and the all reduce. And let's talk about doing those on the mesh and the wafer. Interprocessor communication. So the wafer is a data flow computer. It has pre-routed virtual channels. The messages are sent by sending out data on a virtual channel, which knows where it's going. That's part of the compilation process. There's no on-the-fly message handling and analysis. There's no software. This is all done by hardware. The packet size is 1 word, 32-bit word. It's single clock latency. The time it takes to traverse K processors is K clocks, just under a gigahertz clock rate. Arrival at the destination triggers a task. If the processor does 1 task at a time, so whenever a task ends, 1 clock later, it can start processing the task triggered by anything that's arrived and is sitting in an input queue. That's why data flow, right? That token triggers a task. When the task starts, the data that it's working on just already sitting in register 2. You don't have to even do a memory reference to get at it. There are these 24 colors or virtual channels. The communication is flow controlled at the link level. You never lose any packet. And these communication operations are built into the instruction set. So no PCIe, no MPI library. Instead of microseconds of delay, we have a nanosecond latency. And the links can sustain 1 packet. Say, 4 outgoing links, 4 incoming links, they can sustain 1 packet per clock. Well, to do that communication exchange, what I need to do, let's say I'm the man in the middle. I need to send vector of mine to all 4 neighbors. So I inject that vector on color yellow, which has been pre-routed, and broadcast is possible in the router. So yellow packets that come in from the memory are sent to all 4 cardinal directions. Meanwhile, we've allocated colors in a clever way here so that my 4 neighbors are sending on different colors. So while I send my data out 4 ways, I get data in from each of the 4 other directions labeled by its color, and I can respond to them appropriately. The task that handles turquoise knows what to do with turquoise, namely multiply it by the coefficients that belong to that neighboring direction. All right, so when we write the code for this, this is a diagram of the running code. There's no physical thing. This is a notional concept of the code. We have vectors in memory, including the weight vectors that multiply the data vectors. Right? These are the diagonals, my local diagonals of the matrix A, pre-stored. This is my local data, that vector of in-memory grid point data, which I send out. I also consume it. I have to use it for 3 vector operations corresponding to the 3 grid points in the middle and in the plus and minus direction in the Z axis. 2 of them multiply weights, and we've diagonally scaled, so the guy in the middle doesn't get multiplied by anybody. The products of those weights and incoming vectors, or my own vector, suitably shifted, have to then be added together to make the result. And normally you would do that one at a time, do a vector multiply add, then another vector multiply add, but the data don't come in one at a time, they come in interspersed. The router delivers these colored data whenever it wants to. So what we do is launch background threads for doing the multiplies and a background thread for adding the results. And we connect them through FIFOs. And these threads and FIFOs are controlled by devices in the processor called data structure registers, which are state machines. So when you launch a vector operation, you can either launch it synchronously and let it run before you go to the next instruction, or you can launch it as a background thread under the control of a data structure register, which will steal cycles in the data path whenever you have data ready. Whenever a thread has data ready and something to do, it'll grab a cycle in the data path, make a little progress. The DSR will keep track of where it is. It's total data flow, both globally as wavelets arrive and trigger tasks, and locally within the processor as operands become available and you make progress on these background threads. And there's a way to synchronize the threads. When a thread finishes, it can trigger a task, which is blocked until then, and you get it all straight that way. We write this by hand today. We're working on compilers that will write this for you. The all reduce is fascinating. The all reduce in a machine of 600 by 600 dimensions, clearly by information theory, it can't be done until the information that started here makes it all the way to here. So the diameter of the machine, which is 1200 clocks, is sort of a bound on the all reduce time, lower bound. And we're able to hit it. And we do that by doing reduction along the blue dimensions in parallel. So send, add, send, add, send, add. There are little cartoons of this happening on the sides. Send it along all of the horizontal lines to 2 columns in the middle. Then once they've got what they need after 300 clocks or so, they start doing send adds toward the middle. And finally we get the sums of 4 quadrants down here. Then they do whatever they have to do locally, and then do a 4x4 all reduce, and then broadcast the results back along the red directions. And we're able to hit 1.3 microsecond all reduce across 350,000 processors. It's 850,000 in CS2. It was 380,000 processors in CS1. So it'll be closer to 2 microseconds in CS2 because it's about a 900 by 900 mesh. Well, it's kind of remarkable. And all reduce has been a bottleneck in scaling up Krylov subspace. Not here. Well, the result is, here's the same kind of problem, but only 600 cubed on a conventional machine with up to 16,000 cores. So this is a much, much bigger piece of hardware here than ours. This is multiple racks of a sort of state-of-the-art top 500 machine at Nettle. And they can get down to on the order of 6 milliseconds per time step. Per iteration of by CG step. We get 28 microseconds per iteration. So we're like 200x faster and they're hitting strong scaling limits here. So we're 200x faster and maybe 100x faster than anything they could ever get to with a cluster. Why? Because, clusters is not a great machine for this. The memory bandwidth is inadequate and the communication latency is too big. Strong scaling becomes possible because of the fine granularity. That's the interesting news. Here's a projection of the whole CFD model based on a model of performance that shows that we're like 3 orders of magnitude better in terms of energy cost to do this whole CFD thing. So let's say, where does this leave us? We have 2 things going for us. We have an HPC AI optimized architecture in this no bottlenecks, all hardware communication, no memory bottlenecks. And we have huge compute, huge bandwidth, great flops per watt on the wafer. Well, of course, there's always a catch. Catch 22 is the memory is not huge. 40 gigabytes on CS2, the new 7 nanometer wafer. 40 gigabytes for a machine with petaflop performance is modest. This raises a question. What can you do about that? Well, and I've showed you this before. This is the petaflop days just to train these gigantic neural networks. This is the model size in gigabytes. And here we are at 40. That's a lot of bytes. What can we do? Well, remember I told you about this pipeline training in which we have all of the layers active all the time. In order to do that, we had to store the activations at the layers until the gradients came back, because gradient meets activation to create weight gradient and update weights. That's how learning works. So we have a lot of activation storage in that method. In fact, we have naively ordered d squared, where d is the network depth, number of layers in the neural network. Well, we figured out ways to do better. We're looking at layer at a time. So mini batch stochastic gradient descent approach is layer at a time, where we only have to store 1 activation per layer, and that reduces us to order D storage, big win. We don't have to store all of those. We could divide the network into square root of D chunks of length square root of D and store square root of D activations, then recompute as needed for the intervening layers. So that gives us like only a 30% growth in 1/3, 4 to 3 growth in compute and a big reduction in storage. So that's a good idea. Finally, some networks have the property that the operation of a layer is one-to-one onto. It's an invertible function. So if I don't store anything, go all the way to the end, then I can bring the activations backward along with the gradients, reverse the layers, get the input activation, and compute the weight gradient on the fly, and that reduces you. So we're trying all of those algorithmic tricks, and this is just an opening to the idea that, yeah, there are going to be things we can't do with this storage. You'll have to wait to a future in which we have some way to get more memory. Not there yet. But in the meanwhile, there's plenty of ingenuity. that can be applied to do more with the wafer. And for example, Nettle is very keen to use this to do simulations that fit and achieve real-time behavior, real-time something that's really out of the question with a conventional system. And this thing, by the way, is only 1/3 of a rack high. It only consumes 20 kW. So last year, there was a lovely paper by Charles Lysen and others in CACM called "There's Plenty of Room at the Top," meaning as Moore's law ends, we'll work on software algorithms, hardware architectures, and there are lots of good things. And we think that's absolutely right. And in fact, we're very much doing these things too. But I think our point is there's still room at the bottom. I'm going to hand over to Natalia at this point, and she will take you further and talk in particular about how we can deal with sparsity in training. And I'm going to click stop share and hope for the best. Natalia, it's your PowerPoint.
Thank you, Rob. Hi, everyone. So I would like to talk a little bit about what it all means for deep learning. So my background and my expertise is mostly in machine learning. So I'm interested in seeing what that architecture means for deep neural networks and how we can leverage that architecture to kind of train larger models at a lower flops cost. So I will show once again the plot which Rob showed about sizes and memory and compute requirements of state-of-the-art NLP models. So yes, these models are probably the largest ones which exist today in computer vision and other fields. Typically, the models are smaller, but I think as we progress to this self-supervised mode of pre-training, we see similar models trying to penetrate also other fields as well. And I think in general, there is an observation that if you have enough data, typically you can get to better results with the higher parameter counts. So those models which we train today, they are hugely over-parameterized, they are typically dense, and they take a lot of compute to train them. And they grow essentially exponentially in both memory requirements and probably what is even more important in compute requirements. So for memory, you can do different tricks. You can offload parts of the model outside of accelerator. You can do different things to still feed that model into the training. But for compute, we can't do anything. So it takes enormous amount of time and enormous amount of effort to train those beasts on distributed architectures. But there is kind of one promising trend, and I would like to point to this kind of orange thing. That's one configuration of a switch transformer model, which is the largest one is I think the largest one is the largest model ever trained ever, 1.6 trillion parameters. That's a little bit smaller one, but you can see that although in size, so in the model capacity, number of parameters, it's essentially larger than something like GPT-2, significantly larger. But in terms of flops required to train that model, it's incomparable to that. And the trick there is that you don't use dense regime to train that model. So you use tricks like conditional computation to choose which data points are used to update which parameters of the model. So essentially, you get the same parameter count at a lower cost. And I personally believe that that's the way forward. So we still want those models to have greater capacity. We still want probably to grow parameter count, at least with the existing way how we train them. But we want to find the ways how to train those large models at a lower cost count. So the question is, how can we continue increasing model sizes, but without blowing up the compute? That's a very active area of research. There is a lot of methods which show how you can reduce essentially flop count to accuracy. And I know that your group is working on one of those on sparsity. That's, I think, one of the very promising directions there. So how we can induce sparsity either in data or activations or into model, into weight sparsity. And there are different approaches how you can do that. And sparsity induction essentially helps us to reduce flop count to train larger models. Another idea is, which you can argue another instantiation of sparsity, leverage of conditional computations, which can be kind of coarse-grained, like in switch transformers, when you decide which branch of the model should be used for a specific input sample, and kind of which parameters should be influenced by which input data. Or it could be fine-grained, like in universal transformer, where you do that in a much kind of finer granularity. You can do that decision based on like per batch, or even per sequence, or per token, or per pixel. So essentially, when you decide which parameter of the model should be influenced by which slice of the input data. And those approaches have been shown to reduce these flops to accuracy. The tricky bit is kind of how to translate that reduction of flops to accuracy into reduction of training time to accuracy. And one other thing which we are also looking at Cerebras is also looking at optimal batch sizes, which are used to train those models. We believe that today, because you are forced to use highly distributed systems to train those large models, people usually use large batches, which are much larger than they are required to be to train those models. So essentially, you forced to increase number of epochs to train a model to a certain accuracy, and you can do better if you can utilize hardware with a smaller batch. So that's another, I think, area of research which also can help us to reduce kind of these flops to accuracy method. But then the question is, again, okay, we have these algorithms, we have these all areas of research which shows how to reduce flops to accuracy, how we can translate that to reduced time to accuracy. And for that, we need very flexible hardware. So Waferscale Engine has been designed to do exactly that. And I think there are kind of two key properties of our engine which well position us to kind of enable explorations in all of those algorithms and helps us to translate that reduced flops to count, flops to accuracy to reduced time to accuracy. The first one, Waferscale Engine, is a data flow architecture. And Rob talked about that a bit, how that works. But essentially what that means is that we have flexibility to stream data at a very fine granularity. So we can inherently harvest sparsity either in activations or in weights. And I will talk a little bit how we do that. And the second key property is that you can think about Waferscale Engine as a essentially multiple instructions, multiple data architecture. It's not completely true, so we still have SIMD engines at every PEs, but we have very large number of processing elements, and all of those processing elements can be programmed completely independently, and they can perform different operations in different data. So it gives you much more flexibility. You are no longer kind of required to try to do when I'm talking about just matrix separation, to try to do to find the blocks of like dense blocks of those matrices, so you can do the same operations on different data. So those two key properties enable us to leverage multiple techniques, and we hope, I believe that that's one of the key properties of the Waferscale Engine, which will enable us to train faster, larger models in the future. So talking a little bit more in details about what do we have on every processing element and why it's good for this conditional computation, and why it's good for sparsity, and expanding on kind of what Rob has covered. Again, one of the key properties is that all of those cores, 400,000 for the first generation 16 nanometer chip, and around 800,000 for second generation, they're all individually programmable. So they have a full array of general instructions, so branching, whatever you need, and with also extensions on for tensor ops. So extensions for the operations which are most commonly used for training and inference neural nets. Then we have this massive memory bandwidth, which essentially enables us to have full performance and the complete utilization of the chip on all blast levels, starting from AXP example that Rob mentioned. And that gives us an ability to kind of work very flexibly on those types of algorithms I mentioned. The data flow scheduling is supported in hardware. Rob mentioned that too. So we kind of everything, the fabric is programmed during the compilation time. So there is no context switching happening during the execution. Every route is also programmed during the compile time, so there are no overheads. Essentially, we have also kind of support on the hardware to do to retrieve relevant data from the local memory for all of the computations. And when it comes to sparsity, essentially the default representation format for all the data which travels on the fabric across the chip is sparse data format. So sparse data is natively represented in compressed sparse row. That means that essentially we don't send 0 elements across the fabric and we don't process them at all. Whenever we have 0 results, they are automatically filtered out before being sent to the next processing element to do the next operation. And they are not received, and we don't do any operations on sparsity. There is one caveat though to this. So there's this intrinsic ability of the hardware to, how we call it, harvest sparsity, applies to only one operand in your matrix vector or matrix-matrix multiplication. So essentially the data which arrives on the fabric can be sparse. Again, it's represented in sparse format by default. And you need to program, obviously, the core to do the operations in the right way, but it's very straightforward. And essentially, after you've done that, you don't have to do, like, it's very easy to translate that to speed up. But the second operand is typically being read from the local memory of the chip. And there we, at least today, typically assume that that operand is dense. So what it brings us that when we talk about 2 different modes of kind of sparsity induction in training, when you train neural network, either inducing sparsity into activations or into data, or inducing sparsity into weights, we can support both of those, but with different execution modes on the hardware. So today, the default execution mode on CS1 and CS2 systems is when we have kind of stationary weights and we stream activations through the fabric. What that means is that we distribute all parameters of the model across the chip, and they're being stored distributedly in the local memory of the chip, and the data is what arrives through the fabric. So this gives us an ability to, again, without any effort, to harvest sparsity inside activations and inside deltas. There is obvious limitations to that approach, not only because we can fit only models up to a certain size onto the wafer. We still have memory limitations, as everyone else does. And also, it will require much more programming effort to harvest sparsity from weights. So the second execution mode is when we flip the model. So we keep activations stationary or data stationary. That's much more like how GPU executes training today, when you load a mini batch worth of data into the local memory of the device of the accelerator. And then we stream weights through the fabric. In this mode, since we flip that, we have an ability to also harvest sparsity from weights, and that can be very fine-grained sparsity. It will still be translated into speed up. So usually today we use the first execution mode for smaller models, which can fit completely onto the chip, and we are actively working on the second execution mode for larger models. So we have a prototype working at the lab. And to give you just one justification that the whole thing works, I have results from experiments, completely synthetic experiments of measuring how sparsity translates to speed up in case of this pipelined execution. So that's where weights are stationary and weights are expected to be dense, but we induce sparsity into data, into activations. So what we've done here, we constructed a completely synthetic model. It's a fully connected model with a bunch of layers. I think quite a large model. It was around 700 million parameters, just a bunch of fully connected layers. The first was, again, completely synthetic thing. We used identity, not linearity, which doesn't make sense from the ML perspective, but served the purpose for this experiment. So we know that identity doesn't induce any sparsity into the data. And we choose their throughput of the system on that model as our baseline. And we see how much acceleration we can get on top of that without changing any code, without changing anything, but just changing slightly the model. So changing the code of the model, not changing the implementation of the cores and microcode which runs on the system. The first step is we replace that identity nonlinearity with the ReLU, which zeroes out all negative numbers. So you have this natural sparsification of data as it goes through the network. And instantly we measure speed up on the hardware, again, just by replacing that activation function, because now we are not doing their matrix vector multiplications from the layers which are following up the ReLU, so on 0 elements, which goes from the previous activation layer. And then we started to kind of synthetically add more sparsity on top of that. So we just randomly knocked out 25% of activations at every single layer and 50% of activations, and essentially looked how much we can translate that to acceleration. So that experiment proved that hardware is capable to translate sparsity into speed up quite reliably. The only thing we now need is to understand what's the optimal sparsity induction methods that make sense from the machine learning perspective. And we have a team actively working on that and following all the research results in specifications of models, both when we try to specify data and weight. So we have all the tools. We have the hardware, we have the low-level software, which can translate sparsity into speed. Now we need to understand what's the best policy to induce that sparsity during the training procedure, so we can still train the model to the target accuracy at higher speed. So kind of summarizing, I think for the field of deep learning, we need not only larger models, but we need what I call smarter models, so smarter techniques how to train them. So larger models doesn't translate to kind of a linear or even super linear requirement in flops to train those models. And in order to be able to leverage algorithms which allow you to reduce computational complexity of the model of the training process, we need flexible hardware to translate that into speed ups on actual training time. So we have built a special purpose chip system to power, cool down, and bring data to the chip, and software, which enables us to do a lot of experiments with those types of models. So it's a very powerful single node and can replace a medium-sized cluster of a GPU, so you don't need to think about distribution. But probably what's even more important, that's flexible and dynamic. So it enables research on these fine-grained sparsity and conditional dynamic techniques, which aims to reduce time to train through reduced computational complexity of the models. And we hope that by introducing this new type of architecture, we will encourage researchers to come up with the new types of models, new training techniques, new ideas how to induce sparsity or use other methods to reduce computational complexity of the model, which can be then translated on the chip into faster training. Thank you.
Thank you.
Thank you, Natalia, Rob, for the lovely talk. Before we go to questions, I want to just mention that this was the last BCast talk of our current season, and we'll have a short summer break and pick up with more BCast in July, starting with Bronis Sapinski, the Chief Technology Officer of Livermore Computing at Lawrence Livermore National Lab. And check our website for more details on that.